welcome you to another Theory of Statistics class. And of course, today the focus is we are going to be on chapter 4 that we call the probability distributions of continuous random variables. And of course, we advise that you listen or pay attention and ask questions where necessary. Of course, my TA is going to walk you through some work examples in the lab, and we advise that from time to time you attend the lab. Okay, so we're starting probability distributions of continuous random variable. Today, I remember the other time I told you that we got two types of random variable. We got discrete random variable, and we got continuous random variable. All what we've been doing all this while, we'll be focusing on discrete random variable. Okay, with discrete random variable, of course, I remember walking through binomial, negative binomial, geometric Poisson distribution. All of that are classified under discrete or probability distribution. Well, let me tell you this, most of real life phenomena can actually be modeled by continuous probability distributions that we want to start today. Instead of us to be focusing on just a single value, we actually going to be focusing on values within an interval. So which means we're actually going to cover all values within an interval. Let me tell you this. If you want to talk about whether in economy or whether in environment, whether in medical field, most of the variables in that very area follow continuous probability distribution. If I want to measure inflation rate, if I want to answer a statistical question that has to do with inflation rate, okay, of course, the appropriate probability distribution will actually be continuous type. If I want to talk about blood pressure, if I want to talk about income, of course, in this chapter, you're going to be hearing different kind of probability distribution, like normal, like exponential, like Weibull, and so on like that. So they're going to be in focus. Okay, so for you to be able to understand what's going on, okay, according to Kolmogorov axioms, okay, we actually expect continuous probability distributions to have some properties. Okay, so I'm going to walk you through all of that. Okay, so let's get started. Okay, like I said, I need you to pay attention to this guy. Okay, if because of the fact that we're no longer going to be working with a single value, because the probability that a continuous random variable will take an exact value is 0. I'm going to say that again. The probability that a continuous random variable can take an exact value, okay, is 0. So what we normally do, we consider values in the interval, and whenever intervals is involved, our focus will be on density. Okay, if you take a look at what I'm to show you now. This is a density plot. Okay, this is a density plot. We believe if I want to figure out the probability in the interval A and B, I got interval A and B. We believe S is a continuous random variable. S lies between an interval A and B. If I want to figure out the probability of occurrence in that interval, I should be ready to perform an antiderivative. I'm going to say that again. We don't just do what we do. We got a reason why we do what we do. We don't just do math. We don't just do calculus. So we're going to do calculus because we want to figure out the total area under a curve. The total area under a curve is I want to figure out the probability of a random variable in an interval A and B. Okay, if I want to do that, I need to identify a function, which is f of s. Okay, as you can see, that f of s. And what I'm going to be doing is performing this. Take a look at that. I want to find the probability of s lying between A and B. I may want to find the probability of a blood pressure of my patient lying between a particular, between A and B values. Of course, I should be ready to perform an antiderivative. Okay, so that's why you see, you're going to see integral. Okay, integral, A to B. Okay, the A and B, they are the limit of the integration, and of course, they're going to serve as, the limit of the interval, and the f of s is actually going to be whatever function that is of continuous type. Okay, so, when you take a look at the whole density plot, okay, we are not interested in everything because if I'm interested in everything, I'm going to be talking about getting to the tail end, but I'm only at times will be interested in interval A and B. So and that is exactly what you're seeing. And of course, please pay attention, take a look at this. I'm trying to say I have a function, okay? I'm actually mapping, okay? I'm mapping, at the end of the day, my probability, value that I'm actually going to have should be between 0 and 1. But at times, we could have a function, where the random variable can take a value, okay, in that interval. Okay, I'm actually moving. Now, we have a Kolmogorov axioms when it comes to continuous probability distribution. Of course, I remember when we're dealing with the discrete, okay, the first Kolmogorov axioms, whether discrete or continuous, is that the probability associated with the event must be non-negative, okay? And that's exactly what I'm trying to say here. Take a look at that guy, okay? Non-negative. I think what I'm going to do, let me do this so that when I want to write, then I'm actually going to put that down. Okay, let me put that for now. Okay, so the first one for the continuous type, they have to be non-negative. You know what that guy, what this guy is talking about, this guy? That guy mean for every x in real number. For every s in real number, okay, that condition must be satisfied. That's exactly what we mean. Now, I remember when we're dealing with the discrete, okay, in the discrete, we normally say the probability of a sample space must be equal to 1, which we call the normalization. But you know what? In continuous, okay, in continuous, it has to be integral, f of s, ds, over the range of whatever interval we're considering must be equal to 1. Before doing anything with the probability density or the probability function of the continuous type, okay, this condition must be satisfied. And you know what that means? It means the total area under a curve must be equal to 1. Total area under a curve must be equal to 1. If I consider all the state space, it has to be equal to 1. F of s, ds, has to be equal to 1. And if that happens, then I can go ahead, I can find the probability of a random variable lie between A and B. Okay, I can find the probability in a weather, or what is the probability that tomorrow's weather is actually going to lie between maybe 68 and 75. Then I'm trying to say, that weather, it's a continuous type that we can seek redress in an interval. Okay, I'm moving. Now, based on what I've reading, take a look at this. For a continuous random variable, in a continuous random variable, we don't talk about this guy. Please pay attention. We don't talk about this guy. But we talk about that in discrete. Okay? We don't have a situation where the probability of s is going to be equal to s. Like, I can't find the probability of s equal to 5. I can find the probability of S equal to 7 for continuous, but we can do that for discrete. And that's why we said, okay, our probability, the F of S here, we're using that as a probability density function. I'm going to say this. A probability function for discrete random variable, we call that probability mass function. But for continuous random variable, we call that probability density function. So whenever you hear probability mass function, we're referring to the probability of a discrete type. When you hear probability density function, then we're referring to continuous random variable. So, and the probability of S equal to an exact value is 0 for continuous. But it is not, it may not be 0 for discrete. Okay. And of course, please, I need you to pay attention to something. Take a look at this guy. When I'm talking about continuous, whether A is, if you take a look at this guy, you take a look at this guy, if you take a look at this guy, and if you take a look at this guy, they are all the same for continuous random variable. They are all the same. But they are not the same for discrete. But they are all the same for continuous. Please take note. They are all the same. That's what I mean. Okay, I'm moving. I'm actually going to move right now. Now, I need you to pay attention. Okay? I totally agree that it's getting tough. Okay? But you know what? If you sit back, pay attention, ask questions, where you get stuck, you're actually going to be fine. Okay, let's take a look at the first one. All of these are density plots. But our focus is different in all these graphs. Let's take a look at the first one. In the first one, every area is shaded. When every area is shaded, then I should be able to have 1. Because the total area under a curve equal to 1. Does that make sense? So, take a look at that. What is the mathematical implication of that? Okay, if I want to go by fundamental theorem of calculus, that's what I mean. Okay, integral negative infinity to infinity f of s ds must be equal to 1. But we got situations where we may not be interested in all. Take a look at the second one. We're not interested in all. We're only interested in the interval A and B, only the shaded parts. That guy actually means I want to figure out the probability of S lie between A and B. I'm not interested in the total parts. Then what do I expect? Then I expect my probability value to be less than 1. Because when I'm interested in the O area, I'm actually going to get 1. But when I'm interested, when I truncate, when my interest is not on the whole area, then I expect my probability value to be less than 1. Take a look at this guy. At times, the interest may be on one of the tail head. Okay? If I'm interested in this side, only shaded part, and here, this is from B. This is starting from B and above. Then it means I want to find the probability of S greater or equal to B. But let me tell you this. The probability of S greater or equal to B is the same as probability of S greater than B when S is continuous. Please take notes. The two of them are the same. Okay? So in that situation, I'm actually going to start from B. That's why I'm starting from B. I'm going to go to the infinity, depending on the upper bound of that particular function. Okay? Now, at times, we may be interested in the left side. Take a look at this guy. We may be interested in the left side. In the left side, okay? If I'm interested in the left side, okay, S less or equal to A. Okay, this is A, then less or equal to A. Okay, I'm actually going to start from the lower part of the function. The lower part of the function is actually going to be given. Here, I'm assuming, okay, the lowest part in the world is negative infinity. But that depends on the function. then I'm going to get back to A. Okay, similarly, okay, the probability of S less or equal to A is the same as the probability of S less than A for continuous random variable. Okay, they are the same. Now I'm moving. Now I want to walk us through an example now. Okay, suppose that the error in the reaction temperature, okay, is centigrade for a controlled laboratory experiment. It's a continuous random variable S having the following probability density function. Okay, mathematicians, they've actually provided us a way to model errors. Okay, we can't do without making errors. We live in a stochastic environment where, there's always going to be a gap, between our model and reality. Okay, how do we measure that gap? And that's why, if you take a look at this guy now, so the belief, the mathematician have come out with this. Please pay attention. I want to explain this guy. Okay, this guy is trying to say f of s equal 1 over 3s squared, okay, provided s lie between -1 and 2, and f of s equal to 0. 0 means it does not exist, okay, if you are considering a range outside -1 and 2. Okay, let me tell you this. If you like Minnesota now as a map, okay, Minnesota is defined, okay, under the map. Okay, the moment if you are outside the map of Minnesota, you are no longer in Minnesota. That is what this guy is trying to say. Oh, my f of s, my function is only defined, okay, my function is 1 over 3s squared, provided s lie between -1 and 2. X where, if you take a look at this guy now, is trying to say my function does not define if my s is outside -1 and 2. That's exactly what he's trying to talk about. Okay, now, if you have this, before I can use this function or this continue, the fact that I have it in an interval has given me an indication that this is a continuous function, because I have s lie between -1 and 2. That is an indication. Okay, in this class, if you are working with discrete, we normally have a table where they're going to give you when s equal to 1, 2, stuff like that. But in the case of continuous, you're going to have it in an interval. Okay, now, before I can do anything meaningful with this probability function, okay, I need to first verify whether this is a true probability functions. We could have functions. Functions may not necessarily be a probability function. But how can we verify if a function is a probability function? Then we're going to go by way of Kolmogorov axioms. Now, number one, we want to verify, is this function non-negative? Okay, is it non-negative at a given, interval? Now, take a look at -1 to 2. If you plug in any value in the interval into something squared, can you see this squared, right? Okay, if you plug in anything, the result is going to be positive. That's a way to verify. Number one, you verify non-negativity. And after verifying non-negativity, can we also verify the probability of normalization? Can we also verify when I integrate the function over the range? The range is going to be from -1 to 2. Does it give me 1? If it gives me 1, then I'm actually going to say that is a valid probability density function. Go ahead.
Is there a relationship between the term normality and normalization?
Do you say is there a relationship, or is there a difference between normality and normalization? Is that what you mean?
Yeah.
Wait, did you say normality?
Yes.
Okay, this is what happened. Normality is not normalization. But by normalization in axioms is if it is a discrete random variable, when I sum the probability function, does it give me 1? If it is continuous, when I integrate the probability function over the entire state space, does it give me 1? That's a normalization. But that is not normality, because we're still going to talk about in this class one of the continuous probability distribution is called normal distribution. Have I answered your question? Okay, now let me tell you this. It is only when this old that we can begin to find probability using the probability function. Okay? Now, I want to show you how that's going to hold. The investigation now. Okay? Now, I needed to pay attention. Okay? I've already told you. Number one, assumption is verified because that very function, when you plug in any value, is going to be a positive. Take a look at the function. Can you see that? If you plug in any values in this interval, whether negative or positive, okay, you're still going to have positive because of s squared. That's quadratic in nature. Okay, now that the first one is verified. Okay, the body second one is what I'm trying to do here. Okay, look at the formula that I'm using. Okay, what am I actually doing? This is what I'm doing. I want to integrate the function given over the state space. What was the state space? It's from -1 to 2. That's why I say -1 to 2. I know you've come across these in your high school. You do a lot of these, but you don't know why you're doing it. That's okay. You know, my daughter, nobody asks me, my daughter in high school, what is the essence of this? But let me tell you this. The essence of this is not the original form. This is actually coming from a real-life problem. Okay? This is talking about the error in the reaction temperature. A mathematician has already looked at the situation, and the mathematician has created a model. Okay, so this guy now is more or less like a model. Okay, this is like a model. This is trying to tell you the minimal error ever they can make, is going to be -1. The maximum error they're going to make is 2. Okay, for the error they can make is going to be between that. Maybe he has studied scenarios and record errors. Errors is actually going to be in this state space. And if I know that, I should be able to conduct, any statistical inference. I should be able to answer a probability question or statistical question. Okay, so in the end, look at what I've done now. Because this guy gave me 1, then it makes sense. If you give me 1, that's actually verify that it is a valid PDF. I can ask you to verify. I can give you a probability function, a continuous type, and ask you to verify. So right now, because of the fact that this guy holds, okay, then I'm going to say it is a valid PDF. It is a valid PDF. PDF means probability density function. But the moment it is not equal to 1, then it is not a valid PDF. If it is not a valid PDF, what is the consequence? You cannot use that to answer probability question. It is only when it's a valid PDF that you can use it to answer probability question. Okay? Now this is a valid PDF right now. Okay? So the next thing that I'm actually going to talk about, I can now use it to answer a probability question. Okay, maybe I don't want to go from I don't want to consider the entire range. I don't want to go from -1 to 2. Okay, maybe I want to truncate. I can use that to answer whatever question. Right now, I want to find the probability that's going to be between 0 and 1. I can find that because I've already verified that this guy is a valid PDF because of the fact that the normalization axioms hold. Now, what I'm going to do right now, I'm going to perform my antiderivative, okay, when I'm done, over the range of 1 and 0. You've done all stuff like this before in your high school, but right now we're just trying to relating it to real life. Now, let me tell you this. After you're done with this, you get 1/9. If you want to make a sense out of the 1/9, okay, if you want to make a sense of probability value you got, multiply by 100. Okay, if I do 1 over 9 divided by 100, give me 1 second. Okay, 1 divided by 9, this is like 11%. Now, if I want to make an interpretation here, 11% of the time, the error occurred between 0 and 1. The error that you have is between 0 and 1. That's what that guy means. That occurs 11% of the time. So which means between 0 and 1, you don't have error to occur 100% of the time. But when we have that occurring 100% of the time, okay, it occurs 100% of the time if I consider all the range in the interval. Of course, that is a sure event. That within the range in the interval, the possible range in the interval, the error will occur. That's a sure event. That's why you have 1. Does that make sense? If you want to make an interpretation, or if you really want to enjoy probability, make sure you interpret. Okay, now moving. I just got that now. Okay, and this is the density plot that depict the result that I got. Okay, this is trying to say, okay, I'm only considering, between 0 and 1. I'm not interested in the overall range. Of course, I expect my result to be less than 1, because when I consider the entire range, that should give me 1. But when I actually consider a truncated part of that, I should have less than 1. Okay, I'm moving. Now, another thing we can talk about, one of the properties of a continuous probability distribution is cumulative distribution. Okay, cumulative distribution function. Now, let me tell you this. What is the essence of cumulative distribution function? We use that to obtain probability as well. But in the cumulative, this is the formula. I want to go from the lower bound, and I want to terminate at x. I want to terminate at a particular value of x. But I want to start from the lower bound. Okay, starting from the lower bound. And that was why you see, starting from the negative infinity, okay, up to a particular point, x. This is what we call the CDF, the cumulative density function. Okay, we use this in survival analysis. Okay, what is the probability with respect to whoever they have a terminal disease? What is the probability that it's going to, the waiting time before the certain occurrence is going to be within 10, 5, and so on like that? If you take a look at this, the probability of this is s less or equal to s. So which means I want to consider from, the lower bound up to that particular point, okay, then f of t, the t, and this guy is the same thing as a capital F. The capital F, okay, there's a difference between capital F and a lowercase f. The lowercase f is the PDF. The uppercase f is the CDF. Okay, the PDF is probability density function. The CDF is cumulative density function. Okay, when I perform an antiderivative on the PDF, I'm going to get a CDF. If I want to go back from CDF to PDF, then I should perform derivative. Does that make sense? Okay. Now, I'm going to be moving. Now, take a look at this now. The moment from here, I got this. Then I can find what is the probability of this. What is the probability of S lie between that? Okay, or what I'm going to do is that can be splitted. Okay, the probability of S lie between this and this, I'm going to start with the upper bound first minus the lower bound. And let me tell you this guy is the f of x that I obtain, and I put a b inside wherever I see x. And this guy also the f of x that I obtain, but I put a inside that. Okay, now I'm going to walk you through an example. So we use the CDF also to compute probability. Now, I'm going to show you, take a look at this. you were given this, and they want you to find a CDF. Okay, don't forget, look at my CDF. You see that? I'm going to start from the lower bound. The lower bound in this question is -1 to x. Then, they gave me f of s before. I will change that to t. Can you see this? When I'm done here, this is going to be in terms of x. That's why you have it in terms of x. Can you see that? This is CDF. This is in terms of s. You've considered from the lower bound to the upper bound, x to the x. Do you know if I plug in the upper bound, what is the upper bound? 2, right? If I plug in 2 here, this is going to give me 1. Can you try it? Plug in 2. 2 raised to the power 3, 8. 8 plus 1, 9. 9 divided, that would be 1. Can you see that? Okay, so we use the CDF, and this is the way we're going to write it. If you want to write the CDF, if I'm going to start, this guy means greater than -1. For less than -1 does not exist. That would be 0. I told you the other time that when you are considering something is outside the range, the f of s is not going to be defined. That is why when I say s less than 1, because when you take a look at this, please pay attention. When you take a look at this, you know what that guy mean? That guy mean s greater than -1 and x less than 2. That's what that guy mean. But you know what I'm trying to do here? I want to consider less than. Let's not less than -1. Because of that, that will be 0. Okay? But over this range, I got this guy out. Can you see that? Now, if I want to go against 2, okay, take a look at this. If for s greater or equal to 2, that's going to be 1. So which means I want to use the entire range. So if I want to write my CDF, this is the way we're going to write your CDF. Look at the way I write my CDF. Please pay attention. Okay? If I want to write my CDF, okay, the equation is going to be in the middle. At the tail end, I'm going to go against the interval. Now, going against the interval, look at this one. What happened? For 0, for s less than -1, I say 0. And this is the tail. We're always going to have the two tail end. Okay, 1 we consider when it is less than the lower bound, that will be 0. Greater or equal to the upper bound, that will be 1. And in the middle, what do you have in the middle? The CDF that you got. Okay, so that is how we got that. Okay, and if I want to sketch the CDF, okay, the CDF is going to be going like that. It's an ogie. You see that? It reaches the maximum at 2. The maximum as the upper bound. Don't forget, the upper bound is 2 in this cell. So that's why you can see the maximum there then before it became flat, which means for anything greater than 2, it's still going to remain 1, which is what we're talking about there. It's still going to remain 1. Okay, you can now use that to answer a question. What is the probability? For instance, I want to answer this question. What is the probability of s lie between 0 and 1? I'm going to make use of this. You know what I'm going to do? Okay, I will plug in 1 into that equation, minus when I plug in 0, and that will give me this. I'll plug in 1, and I'll plug in 0. I'm going to plug in 1 wherever. Now, let's plug in 1. 1 raised to the power 3, 1. 1 plus 1, 2. 2 over 9 is this guy. Then, what am I going to plug in? 0. Plug in 0 is 0 raised to the power 3 plus 1 over 9. That's going to be 1 over 9. Then I subtract. Then I got that. Look at that. That's super cool, right? Okay. I want to move right now. I'm moving. Okay. Let me also tell you this. They say, if you see the way I compute here, I compute a CDF for continuous random variable. We can also compute a CDF for discrete. Now, whenever you see a table like this, you're working with discrete, right? Okay, I want to go back to discrete, and I want to show you how we also compute the CDF. Now, take a look at that. We're given that. How do we compute a CDF with discrete? It's different from the way we compute CDF with continuous. With continuous, we do from lower bound to S. Okay, but right now, let's see what you're going to do. Okay, now here, I'm actually starting. For S lie between 0 and 1, is 0 and 1 here, it means because of the fact that you have equality, it means I can consider S equal to 0. Now, on the board, S equal to 0, what is the probability? 10 over 28. Do you see that? Please focus on the board. Do you see this guy, right? That's what I'm writing here. Look at that. Now, I go from that to 1 to 2. I want to go to 1 to 2. Okay, cumulatively. I'm going to cumulate. This guy is trying to say, okay, this includes 1, but I'm going to cumulate from 0 to 1. If I'm going to cumulate right now from 0 to 1, then look at that. From 0 to 1, oh my God, from 0 to 1, I'm going to add those two probabilities. But I'm cumulating. Okay, that's why you see that plus that equal to that. Now, lastly, I'm going to cumulate S greater or equal to 2. It's going to be adding everything. Okay, that is going to be that. And that's why you have this guy here. This is how we compute a CDF when we are working with discrete. Okay, now based on this, how do we present this result? Please pay attention. If you don't understand, ask me a question. How do we present all these results? Okay, how do we present all these results? You see the results? How do we present them? This is the way we present them. Look at that. Whenever you are presenting a CDF, it's going to look like that. At the beginning, that must be 0. At the end, that must be 1. At the beginning, that must be 0. At the end, that must be 1. Okay? And at the beginning, S less than 0, because if you take a look at the table, I do not have 0. I do not have less than 0. I only have 0, right? So S less than 0 is actually going to be 0. Okay? That's why you see this. Then from there, I have 10 over 28, 25 over 28. Of course, you see with the way I got that guy out, when I consider cumulative, 10 over 28, here 25 over 28, and then lastly, that is the cumulative they're talking about. Okay, now after having that, so this becomes my cumulative distribution function for X. I can graph it. This is graphing it. Okay, if you want to graph it, okay, 10 over 28 all the way to 1. Can you see that? Okay, and 25 over 28, 1 to 2. Do you see that? And for 2 is actually greater or equal to 2 is going to be 1. They're all going to be horizontal function. Okay? Has anybody heard about piecewise functions before in high school? Yes, thank you. It's looking like that. Okay? Okay, now, do you know based on that, I can ask you several questions. I need you to pay attention. Several questions can be asked. Take a look at this. Based on this, I want to find this. Okay, CDF of negative is 0.5. Where does it fall in the piecewise? Where does that fall? Yeah? On the first line. Good job. Send me a message for extra credit, and that would be 0. For any number less than 0, they're all going to be 0. The probability is going to be 0. Okay? Then I want to find for 1.5. Okay? I'm going to check where 1.5 lies. Okay? The 1.5 is definitely going to be here. Right? 1.5 lies between 1 and 2. Then I'm going to call that 25 over 28. The last one is saying 3.2. Oh, where does 3.2 lies? Oh my God, 3.2 is going to be here because this guy is greater or equal to 2. Then I'm just going to call that 1. Math is easy. But you pay attention, it's actually easy. If you get stuck, you ask questions, it's going to be easy. Now, let me tell you this. After that, the next thing I want to walk you through is how do we find the mean and variance? We started again. We want to find the mean and variance. Okay? With a continuous probability function. Take a look at this. If f of s is given as that, over the range of that, and f of s equal to 0, suppose that the diameter of a mirror cylinder, has that. Okay? Like I said, you can investigate whether this guy is non-negative. Of course, it's non-negative. You can also investigate whether it is a valid PDF. Of course, this is how to show that's a valid PDF. Integrate the function given over the range under investigation that give you 1. That means a valid PDF. Let me tell you this. If it is not a valid PDF, don't make attempt to use it to find the mean and variance. Your mean and variance will be wrong if the function you are using is not a valid PDF. How do we find the mean? I'm going to show you. See, going there now. Okay, now here I want to find the probability of S lie between 49.8 and 50.1, which means I'm not interested in the entire interval. Then I'm interested in the shaded area. Of course, I expect my result to be less than 1. And that's why you see this guy. Less than 1. Now, I'm moving. Then I will continue I can find the CDF. Okay. I can find that. Okay. Now, I need you to pay attention now. Find the value of k that make f of y a probability density function. Okay, that make f of y a probability density function. Of course, we expect integral a to b f of s ds to be equal to 1, right? And you know what? At times, the function given is not specifically, completely defined. They want you to figure out k. Okay, here we're using y. Let me use y. So what I'm going to do, what was the limit? I'm going to go from 0 to 1. What is f of y? K, y, 1 minus y. The y equal to 1 from the law. I want to figure out k. I can bring k out. If I bring k out, 0 to 1, I'm actually having y minus y squared, the y equal to 1. Then I'm going to integrate that. Review. We advise you to have a recap on your calculus knowledge. So here, y2 divided by 2, y3 divided by 3 from 0 to 1. Then this is k, then equal to 1. Okay, so when you do that, you're actually going to get your k to be equal to 6. I've already showed that here, k equal to 6. And when k equal to 6, then you're going to rewrite your function again. Rewriting your function, you're going to put back k. You're going to put k here. You're going to put 6 there, which means your function is now 6y, 1 minus y. Okay, that is your function now. That is your new function, where y lies between 0 and 1. Okay, now you can use it to answer. Now, take a look at this. You can use it to answer this question now. There's no difference between the two when it comes to continuous. Do you see that? There's no difference. It's going to give the same result. Okay, you integrate your function, you plug in 1, you plug in 0.4. Okay, but there's what I'm actually going to do before I go. That's what I want to do. Please pay attention. Like I said, pay attention. Look at C. Look at D and E is also the same for continuous, whether less than or less or equal to or that. But take a look at this. I want to find the probability of y less or equal to 0.4, please pay attention, given y less or equal to 0.8. Okay, please pay attention. Okay, this I can use the idea of a conditional probability. The probability of A given B is probability of A, okay, intersection B, you remember, divided by the probability of B. Okay, so if I want to do this one now, I'm actually going to say, what is that? Y less or equal to 0.4, okay, intersection, okay, y less or equal to 0.8, okay, divided, okay, this is the probability of that. Now divided by probability of B, the probability of y less or equal to 0.8. Now, what do you think is going to be common? What is common between this guy and that guy? This one is common, right? Okay, if that guy is common, then I'm just going to do y less or equal to 0.4 divided y less or equal to 0.8. So which means what I just need here, okay, what I just, so what I just need here, okay, I need to follow first. Okay, so I'm actually going to say the probability of y less or equal to 0.4, okay, giving y less or equal to 0.8 equal, okay, now I'm going to do integral, okay, less or equal to 0.4. I'm going to start from the lower bound. What is the lower bound? 0, okay, 0. Is 0 to what? Is 0 to 0.4. Is 0 to 0.4. Or 6y1 minus y, the y, then divided by the second one is 0 to 0.8, 6y1 minus y, the y. That's what I'm going to do. I'll just get my result. Okay? If you work it so good, you're likely going to get, if you're likely going to get that. 0.33 something, if you try that, okay? Then I think I put some exercise there. This is the solution to the exercise. You can try that. And let me see my time. Okay, I say I have 3 minutes. Now, how do I find the mean? Okay, this is the formula for finding the mean. Expected value of s, integral s, f of s, ds. x, f of s, ds. I'm giving this now as f of s. Okay, how do I find the mean? S, f of s, ds. Look at what I've done. Multiply s by the function. Then I'm going to perform the antiderivative. Can you see that? Simplify. At the end of the day, through that, I got my mean. That's my mean. Okay, if I want to find the mean for continuous, it's going to be integral s, f of s, ds. I'm using the method of movement. S, f of s, ds. I can also find the variance. If I want to find the expected value of s squared f of s ds. Okay? And the moment I get my s squared f of s ds, oh my God, I get expected value of s squared to be that. I'm ready to get my variance, and that will be my variance. So the final thing that I just wanted to take note, if I want to find the mean, it's going to be this. S f of s ds. Use the range. I want to find expectation of s squared, a to b, s squared f of s ds. I want to find the variance. Okay, I want to find the variance, of course. The variance of s, expectation of s squared minus expected value of s, all squared. So here I'm trying to say a to b x squared f of s ds minus integral a to b x f of s ds all squared. That's what I mean. Done. That's all I got for you today. Make sure you all stay safe and have a lovely day. See you on Wednesday.
Okay, so that's good.